and so are these. Because of its flexibility and power, the computer can be used to create a remarkable range of pictures. To see just how that's done, we've traveled to Los Angeles to a company called Symbolics. A good place to start understanding computer graphics is to see what's involved in a simple picture. How about the simplest picture? A line. I can pick 2 points on the screen with this device, called a mouse, and have the computer connect them. Now, this only looks easy. Behind the scenes, graphics programmers had to solve mathematical problems. For instance, how does the computer fill in the line segment between these 2 points? The answer is that the screen has X and Y coordinates, like a piece of graph paper. Every point on the screen can be identified by a pair of X and Y values. Now, you may remember that there's a general formula for any line in a coordinate system. So, can the computer use the same equation to draw a line on the screen? Well, things aren't quite that simple. The equation describes an ideal line, made up of infinitely fine points. But this screen is made up of a grid of small squares called picture elements, or pixels. You can see them by zooming in on the screen. Pixels are the fundamental unit of a computer image. You can't draw anything smaller than 1 pixel, but you can make a picture by choosing the colors of the pixels. Now, this line segment I just drew is a special one. It's horizontal. So all the computer needs to do is change the colors of a few rows of pixels. But how about a line like this? It cuts across the gridwork of pixels, and you can see the jagginess that results. So, given the mosaic nature of the screen, how do you make a line look smooth? Programmers need to find a way to adapt the equation of a line, which works for points, to the design of the screen, which is based on pixels. It's easier to understand the problem by looking at the edges of a polygon, which is just a set of straight lines connected together, enclosing an area of the plane. Let's get some expert help from Symbolics programmer Bob Coyne.
If we look at these polygons, you'll notice that the edges of them are jaggy. I'll zoom up on them, and you can see that there's a staircase effect. The pixels are either on or off. There's no intermediate value. In reality, if you looked at those pixels, you would want them to be a percentage on or off depending on how much of the pixel was hit by the line, which was the edge of the polygon. And you want that to be represented by a shade of, basically a shade of gray or some intermediate color value.
Let's say this is a grid of pixels seen close up. Here's the edge of a polygon with the inside colored yellow. Some pixels are entirely outside the polygon. They'll be blue. Others are entirely inside. They'll be yellow. But some pixels are straddlers. If you know the equation of the edge, you can compute the percent of the pixel that lies inside. This pixel should be 24% yellow and 76% blue, which turns out to be this color. If you do this for every pixel along the edge, you end up with this smoother looking line. You can see the softer gradient from blue to yellow, in contrast to the jaggies on this edge, where no intermediate color values are used.
This technique of smoothing the edges is called anti-aliasing. It gives you some of the result that you want, which is not having hard, discontinuous edges in your picture.
To get even better anti-aliasing, you can blend the colors across as many rows of pixels as you want. The only limits are the amount of time and effort you're willing to devote to the task. In other words, you face a trade-off. How good does it have to look, and how much time can you afford to compute it? This is a recurring theme in computer graphics. Any problem is really 2 problems. The first is, how can you solve it? Mathematics can often provide an idealized solution here. But the other problem is, how can you solve it with limited computer memory and time? Take, for example, the problem of coloring in a polygon. Mathematics can suggest many ways to do it. But the challenge for graphics programmers is to find a fast way. One fast algorithm is based on the logic function called XOR. It works like this. Say you want to color this polygon yellow. Start by picking a point outside the polygon and connect it to two adjacent vertices to make a triangle. Now, a triangle is the simplest possible polygon, so we can program the computer to color in a triangle very quickly. Then we move to the neighboring pair of vertices, make a new triangle, and tell the computer to reverse the colors inside. What's blue becomes yellow, and vice versa. This operation is carried out for all neighboring pairs of vertices. A mathematical theorem guarantees that by the time you're done, the inside of the polygon will be yellow and the outside blue. Letters are polygons too, so the triangles that are created by this algorithm can be used to fill in letters as part of a flashy company logo. Okay, now we know how to draw shapes on the screen and how to fill them in with the colors of our choice. So we're able, at least in principle, to make terrific pictures. But they would only be still pictures. And the real excitement of computer graphics is motion. Now, animation involves two kinds of motion. The object can move, and so can the camera, which determines our point of view. Now, suppose we want to move our point of view around the side of this cube. Right away, we run into a problem, as demonstrated by programmer Larry Malone.
As you can see, this looks like a perspective image, and it is something that you could get in a drawing. But it's only valid from one particular point of view, because as we can see by rotating the camera, this object is perfectly flat. And it's just the illusion of the converging lines that makes it look like it has volume. On the screen now we have the front face of a cube. Although it looks the same, when we move the camera around it, we can see it has dimension. That's because the depth dimension has been encoded into this object, and so changing our point of view, we can see all the different sides of a real cube.
So, to produce computer animation, we need real objects with depth, or not real objects actually, but three-dimensional mathematical models of objects. Now, it would be extremely tedious to specify all the points of a model in terms of numbers along the x, y, and z, or depth coordinates. So, Symbolics has developed a program called Geometry to make it easier to create a model. There's another program, Dynamics, that directs the action by moving the objects and the camera. And a third program, called Render, simulates lighting in the final animated scene. We're going to find out a bit about each of these programs from its developer, and I'll jump in from time to time to highlight the role of mathematics. We start with Larry Malone, who's using geometry to model a relatively simple object, a goblet.
It'll have breadth and height, and also have depth. We can move around it and see the dimensionality of the goblet. Rather than trying to define the surface in 3 dimensions, what we'll try to do is simply define a rough approximation of the contour of the goblet. We will take these segments that we have and smooth them out with a spline curve.
How can a curve be drawn on the screen? One way to do it is to type in the location of all the points. The problem is, there are an awful lot of them. Computer graphics takes advantage of a mathematical shortcut that allows you to generate a smooth curve called a spline by picking only a few points that approximate its path. First, connect the points with line segments. Then divide these segments into thirds and connect them like this. Repeat this process a number of times. As the line segments become shorter, you can replace them with a single curved line. What you end up with is a spline, a smooth curve whose shape is determined by the small number of points you started with.
This is actually just a two-dimensional shape, simply a contour. But in order to make it a three-dimensional object, we will take this contour and we will rotate it around the vertical axis.
Here's another example of a contour. You can see how rotating it about this axis would create a surface. This is an economical way of making a 3D object. All you need to do is to describe a 2D curve, the contour, and then to rotate it. And rotation is a simple mathematical operation. And here we have, for the first time, a three-dimensional version of our goblet. It's made up of a large number of polygonal faces. This kind of model allows programmers to write fast algorithms. For example, the goblet now looks transparent. To make it opaque, the computer can run through a list of the faces, making each one solid.
We have the front part of the cup, which is closest to the eye, obscuring the piece of the stem and the piece of the base and the interior part of the goblet, and this is referred to as hidden surface removal.
Once we've created an object, we're ready to stage some action in an animated scene. That means repositioning the object in terms of the X, Y, and Z coordinates of the screen. It turns out that just three mathematical operations can be combined to produce a wide range of realistic movement. I'll use a simple three-dimensional star to show you what I mean. An object can be moved or translated along the x-axis. A translation corresponds to adding some number a to the x-coordinate of the star's location. You can also translate along the y-axis. You can scale the entire object. This involves multiplying all coordinates by some number, call it b. Or you can scale along only one direction. This looks like squashing when b is less than 1 and stretching when b is greater than 1. Finally, you can rotate the star around any of the axes. Here around the z-axis, and here around the x-axis. The motions of our little star were controlled by an animation script, the key feature of a program called Dynamics. Craig Reynolds, the developer of Dynamics, has put together a scene with a little more complicated action.
Here's another script that combines some of those motions that we saw in the a simpler example into some more interesting motions. We're modeling an object here that's bouncing and kind of distorting as it comes down. It's a very cartoony sort of motion. But the elements of it are the same simple motions we've talked about. Translation along the vertical, along the y-axis, rotation around that same axis. Scaling in the vertical, and a compensation for that scale in the horizontal, where the object sort of bulges out when it hits. So in addition to the sorts of motion that's happening, the other thing that makes up the animation is the relationships of those motions to time, and that's what this script here shows us. We can see the relationship between the frames up here and the parameters of the operations. Time runs across the picture horizontally. In fact, the numbers in the little box here represent seconds and frames of time. And so each position here corresponds to a different frame in the animation. The two tracks we're seeing here, the top one is the vertical displacement, and the bottom one is the squash and stretch. So start out with the object down at the on the ground plane, and here's where it reaches its highest point and comes down. The discontinuous thing there is where it bounces, and then on the bottom track at the same point, just slightly delayed, is the squash action. The art in describing the motions is sort of being able to come up with a plan how, by composing the simple transformations, the rotations and the scales and translations, how you would come up with the more complicated motions. This is a model of a plate, or perhaps a coin, that's been dropped on a table, and it's spinning around, coming to rest. The motion is actually sort of complicated. It's not a simple rotation. There's a couple of rotations, but worse, the frame, basically the thing is rolling around on its rim, so the point of contact where the rotation is happening is also being animated. So by nesting together a couple of levels of motion, you can get an action like this that is more close to what's happening in the real world.
The shapes we've seen in these animation scripts are more examples of our old friend, the spline. We've already seen that a spline is a smooth curve whose path is determined by a set of points. Now, think of the spline as a stiff, springy material like this. Imagine that it's bent under tension to follow a path determined by points here, here, and here, so that it forms this smooth curve. If you move one of the control points, you'll change the shape of the curve, not just here, but all along its path. You'd get a similar effect if you change the tension on the material. Now, my spring is just an analogy, but these mathematical properties I'm describing make the spline curve a convenient and graphic means of controlling the motion of an object. Here, for example, is a set of 5 splines, each of which controls the motion of one of these disks. The top spline has maximum tension, which produces very abrupt changes in the motion of the disk on the far left. We've relaxed the tension on the bottom spline, and since the effect is distributed along the entire curve, the steep slopes at the center and the sides have been smoothed off. This spline produces a much gentler motion in the disk on the right, which slows down to a stop and then accelerates on the return trip.
So this is an example of how we might actually use the splines in doing animation. We've got here a real simple little motion test of this object just kind of swirling around, going off into the distance. We're describing it as 3 splines in X, Y, and Z. One of the things you notice here is that as this loops around, it's sort of going off the frame, so that's what we'd like to fix. So what we'll do is go in and edit the X spline. So in fact, why don't we zoom in on that portion of the script just so we can see the spline better. And we can skip through the frames, scroll through them, and see that it's here where it's happening, and that corresponds to this control point of the spline there. And then by changing just the value at this one frame, here the X value now is 66 something, and by moving that in a bit, what we do is control what the X position of the object will be at that frame. So let me just goose it around here, and then tell it to record this value in the script. Now what happens is the plot redraws. There we go, the shape changed a little bit there. Now we see that the motion is pretty much the same. We've gotten the object not to go out of the frame here, but otherwise it's doing about the same thing. It's taking the same amount of time and starting from the same place. The vertical motion is the same. So what we've been able to do is affect just a single aspect of it. The ability to make local changes like that is really important in animation, and in fact it's one of the reasons why doing things with computers is a powerful technique in general, because the computer, when it runs the program, will do exactly the same thing each time, and then if you make a change, you know that the one aspect will change, but all the other aspects will be the same. It's a powerful technique because it allows you to, one by one, to get rid of the mistakes, to converge on a correct solution.
This is just a small sample of the tools that are available to design and correct the motions of one object. Under the direction of a skilled animator, motion can be made as realistic and precise as the effort you're willing to devote to it. But animating many objects this way would require enormous amounts of talent and time. So managing the animation of many objects at once is a hot topic of computer graphics research. This is test footage of a symbolic system for animating many objects, in this case, simulating a flock of birds. The ground position of each bird is chosen at random, and the motion isn't specified frame by frame. Instead, there are rules or behavioral constraints that control the motion. Each bird tries to fly along a general path predetermined for the entire flock, and each bird tries to get close to the center. Here the test has been taken another step, which dramatizes a third constraint. Birds shouldn't collide with one another or with obstacles in their path. Because the birds have been given general behavioral instructions, their motion becomes automated. In other words, the animator gives them a character, and then the birds move in characteristic ways. This behavioral scheme is one promising route to automating very naturalistic motion in many objects at once. So far, we've seen how to make three-dimensional objects and how to move them around. But the objects themselves have just been sort of skeletal outlines, what's usually called wireframes. The third step in creating a convincing animation is to make the objects look solid and realistic. That means adding surface characteristics and simulating the effects of light. We can make this wireframe surface look solid by just coloring in the polygonal faces. But to make it look more realistic, we have to add a directional light source and simulate its effect across the surface. Here's a light source, but how do we figure out the shading? One way is to draw a perpendicular line called a normal, pointing away from each face. Then we compare the direction of each normal to the direction of the light rays. The more nearly parallel they are, the more light is falling on that surface, and the brighter we render it. But now the lighting brings out the faces in our surface. We can make it look smoother by using more surface normals, say one near each corner of each face. Then we average these values to produce a blended shading that's more pleasing. Ultimately, we can calculate the normal for every pixel in the image. That produces the smoothest looking surface. But of course, it requires the greatest amount of computer time. There are many other surface properties we could simulate. We might, for instance, transform this dull surface into a shiny one with reflective highlights. Kevin Hunter describes some of the other surface characteristics that can be controlled to render even more realistic objects.
The next thing is to actually change what the surface material properties are, and one way to do that is what's referred to as texture mapping, which allows you to take a texture that you can either create through a computer or bring in from the outside environment somehow, and basically applique that onto your object and make it look more interesting. So for instance, this particular texture, which was computer generated, is, as you can see, the full extent of it right here. We then took that and wrapped that around this particular object here, this sphere, and made a sort of globe-like texture. Then over here, what we did was we brought in a real camera image of wood grain and then wrapped that around the surface itself. And you can see it's still showing highlights from our light sources, but has this nice wood grain pattern in it. Okay, another property of materials is how opaque or transparent or translucent they are, how much they pass light or allow light to pass through to you to see what's behind them. So in this particular example, we have our test sphere. We have a icosahedron behind it. You can see how the color is affected by the surface that's in front of it. Down here, we've changed how the opacity varies across the surface. So near the edges, it is more opaque. Near the center, it's almost totally transparent. And finally, what we've done is a similar thing over here, but what we've done is reverse the effect. It made it more dense in the center, and then had it fade out toward the edge. What we've done is just simply vary the attributes of the surface to give different effects.
The programs we've seen can be used in concert to make a limitless variety of animations. Here's how Symbolics turned a very well-known magazine logo into a television ID. The first step was to model each object with geometry. Next, dynamics was used to design the motion of each object. Scripts were written and then edited until the movements looked right. A separate script was prepared for the motion of the camera along this roadway. Then a test was made that combined object and camera movements. You have to make sure that the camera doesn't crash into things. The next step was to color, light, and texture map surfaces of individual elements. This is the job of render. Finally, all the pieces were ready to be put together. Computer graphics systems will undoubtedly become more sophisticated and easier to operate. But as in everything else computers do, mathematics will remain the ultimate power source. And it's mathematical insights that are helping to make new computer images more realistic or more fantastic than anything produced so far. So you may never see Math the movie, but you'll certainly see more math at the movies.